All right, well, it's time to do the stoichiometry using molarity. So in the first unit, we reviewed, I was going to say learned, but it was really just a review, how to take grams of one substance and convert it to grams of another substance. So to go grams to moles, you simply divide it by the molar mass. Then to get from moles of one ingredient to another, we used the coefficients from the balanced equation and did a mole ratio. And then to go from moles to grams of the new substance, we just multiplied by the molar mass of the second substance. Well, we're going to continue to do the same sort of thing, just instead of using the molar mass, we're going to use the molarity. Remember, molarity is simply the moles per 1 liter of solution. Now, that doesn't mean you always have 1 liter of solution, just like over here you didn't always have 1 mole of the substance either, but that's what we set up as the conversion factor. So with this new kind of stoich, we are going to start out with the volume of our first substance. Remember, you have to put it in liters. Then you can convert from liters to moles using the molarity if you set it up as a conversion factor. Once you get to moles of the first chemical, you simply use the coefficients from the balanced equation to get to moles of the second chemical. And then if you wanted volume or molarity of the second chemical, once again, you'd use molarity as a conversion factor. So it's essentially the same thing. We're just changing one little part. All right. So here's an example. You have 25 mils of an unknown concentration of sodium hydroxide solution. After adding 3 drops of phenolphthalein indicator, which turns pink in bases, you titrate the sample with 0.1067 molar sulfuric acid until the solution is no longer pink and it turns clear. This requires 42.95 milliliters of H2SO4. So what is the molarity of your sodium hydroxide? Well, already you might be getting a little overwhelmed at just all the words here, but just make a list of the numbers you're given. You have 25 mils of NaOH. You're looking for the molarity of NaOH. You know the volume of the acid, and you know the molarity of the acid. So the question is, which chemical do you start with? Okay, the one you know the most about. Okay, the one you're not being asked about. You're being asked about the base because there's some missing information that we don't know about the base. So you're going to start your calculation with the acid in this instance. And remember the other rule of thumb, start with the number that tells you how much. Okay, so 0.1067 only tells us how strong or concentrated the acid is. It does not tell us how much we have of it. Okay, so start with the chemical that we know the most about, that we're not being asked to solve for. And then between these two numbers, we know we have to start with the acid because we're trying to figure out the base. So between these two numbers, which one do you pick? The one that tells you how much acid you have, and that's the volume. Okay, volume in grams tell you how much. Molarity and density do not tell you how much. Those we use as conversion factors. All right, but the first step we got to do is figure out the recipe between the acid and the base. So we got to set up a balanced chemical equation. 2 sodium hydroxides react with just 1 mole of sulfuric acid. And then I write in the numbers I know underneath the chemicals and then what I'm looking for. And suddenly this, once I write it out like this, when I just have an equation and these 3 numbers, it's a lot less intimidating this way than it was in paragraph form. Now, one thing students sometimes try to do with these, they see that they know a molarity and a volume, and then a volume, but they're missing the molarity. So sometimes they try to treat this like a dilution and use M1V1 equals M2V2. But remember, that equation is only for if you're dealing with one chemical, just one. And you're adding water to it, you're diluting it, just the one chemical. But here, we're not diluting the acid or diluting a base, we are mixing them together. We have a chemical equation. So if we tried to use the dilution formula, we wouldn't get the right answer. because for every 2 moles of base, we react with 1 mole of acid. So this is different. It's not a simple dilution. It's a stoichiometry problem. So always start your solution stoichiometry problems with the liters, not the molarity. Just like in a regular stoichiometry problem, you always start with the mass of your substance, not the molar mass. You start with just the flat out mass. All right, so concentration is an intensive property. So it doesn't tell you how much sample is present. So if you are sent to purchase 2% milk, how much should you get? Well, you really don't know, okay? The 2% does not indicate whether to get a quart or a gallon. So in this case, the 0.1067 molarity only tells us the ratio of moles to liters. It doesn't tell us how many liters. Okay, so we have to start out with the volume of the acid. All right, milliliters are no good though. I got to convert it to liters. And then now I want to get to moles so I can do a mole ratio. Well, this tells me how many moles there are per liter. So I go milliliters to liters. Now I'm going to convert liters to moles using the fact that there's 0.1067 moles per every 1 liter of sulfuric. Okay, so I'm just using molarity as a conversion factor. Then I got to do a mole ratio to get over to the base. 1 mole of acid reacts with 2 moles of base. Okay, and I'm going to stop here and get moles of base and then solve for molarity. We know the volume already of the base. Now we know the moles of the base. Notice I don't round here because this is not the end. Okay, now we're going to plug it into the molarity formula and take moles and divide by liters. Ta-da! Our answer, going out to 4 sig figs, since all these numbers had 4 sig figs, is 0.3666 molar sodium hydroxide. So liters to moles, moles to moles, and then moles to molarity. So it's not that much different. All right, here is another one. How many grams of calcium hydroxide are needed to neutralize 25 mils of 0.1 molar nitric? Once again, 2 chemicals are getting mixed together, so we need a balanced equation. And this is a mix of the old way of doing stoich and this new way we're learning. We're wanting grams of this guy, okay? And we're given the volume of the acid and the molarity of the acid. So where do I start? Well, I'm going to start with a chemical that I know everything about, and that's my acid. Which number do I start with? The one that tells me how much. I have 25 mils of it. Convert that to liters, of course. And for every 1 liter, there's 0.1 moles. That's my molarity, 0.1 molar. Now that I have moles of acid, I can convert to moles of base using my coefficients, 2 to 1. And I want grams of calcium hydroxide, so I just use the molar mass. And ta-da, I'm going to go ahead and round it to 3 sig figs. All right, so this is another problem that I put in your note packet, I believe, or your sample problem packet. How many liters of half-molar hydrochloric acid are needed to react completely with 0.1 moles of lead nitrate, forming a precipitate of lead chloride? Notice how we are given moles already, so we don't need to convert grams to moles or liters to moles, because it's already in moles, so it makes it a shorter problem. We do still need a balanced equation, otherwise we won't know the mole ratio. So write out your balanced equation. There's 2 hydrochlorics to every 1 lead nitrate. We know it's half molar hydrochloric. We're trying to find out how many liters it's going to take to go with 0.1 moles of lead nitrate. So this is a precipitation reaction instead of an acid-base problem, but it doesn't matter. These are all the same. Okay, we're going to have to do a mole ratio in the middle. It's the same math either way. This is just shorter because I know my moles of lead nitrate already. So I'm going to start with a chemical that I'm not asked about. I'm not going to start with the acid. That's my goal. So I'm going to start with my amount of lead nitrate. And since it's already in moles, I can jump right to the mole ratio. 1 mole of lead nitrate reacts with 2 moles of hydrochloric. Now I'm going to use molarity as a conversion factor again, but notice this time I need to flip it upside down. Okay, I have moles of acid and I'm trying to get to liters. So I'm going to put moles on bottom and the 1 liter on top. It's 0.5 molar, which means there's 0.5 moles in every 1 liter. That's what I like about using the conversion factor instead of the algebra formula. We don't have to, mess with doing any algebra here. Just flip the conversion factor upside down. And I'm done. Just 2 steps, and I'm at liters of hydrochloric. I went from moles of lead nitrate to moles of hydrochloric, and then from moles to liters. They won't always be this short, but that's a fast one. All right, practice using a pipette. I really probably don't need to go through this very much since you did this in the molarity lab already. We've already done this. Okay, here is a good one. The quantity of chloride ion in a municipal water supply is determined by titrating it with silver ions. The reaction taking place during the titration is silver plus chloride makes silver chloride. The end point in this type of titration is marked by a change in color of a special type of indicator. How many grams of chloride ion are in a sample of water if 20.2 milliliters of 0.1 molar silver ion is needed to react with all the chloride in the sample? If the sample has a mass of 10 grams, what percent of chloride does it contain? So here we got a redox reaction going on, and we're going to do a percentage at the end. So this one's a little different, but the math is still the same. I've got to set up a balanced chemical equation. I'll work this one out with you in class, though, because this is the way the work is shown in the book, and they make everything look more complicated. All right, but that's the answer that you'll get when you do it correctly. All right, here's another one, determining concentration via an acid-base titration. We've done that. One commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide for a short time. Remove them from the sodium hydroxide and spray off the peel. The concentration of sodium hydroxide is normally in the range of 3 to 6 molar. Pretty strong. So it gets analyzed periodically to make sure that it's in that range. In one such analysis, 45.7 mils of half molar sulfuric is required to neutralize a 20 mil sample of base. What's the concentration of the base? Okay, we'll need a balanced chemical equation again, and this is another one that I just want to do in class. And that, my dears, is the end. That means that I don't have a slideshow for the ones at the end of your sample problems that take up an entire piece of paper. Those involve figuring out the amount of leftover excess reactant and the concentration of the soluble ions left floating around in the solution as well. So that'll be a fun day, but I'm not going to try to do that via video. All right, that is it for the chapter, though.